Hello everyone, welcome to the lecture 10 of the course Diffusion in Solids, and this is also our second tutorial lecture. So as I had indicated, every week we will have one tutorial lecture so that you can learn to apply the concepts that we learned over the week, and also it helps you prepare for the assignments. So today we will take some examples of solving the problems on the diffusion equations. So, first question is, let us say we consider a case where very small amount of material B as thin film is sandwiched between two rods of pure material A and annealed at temperature T for time T. Which of the following statements are correct regarding the composition profiles developed? Assuming origin to be the center of this assembly. These are the four options: that the composition profile is symmetrical about x equal to 0, the first derivative is symmetrical about x equal to 0, first derivative is anti-symmetric about x equal to 0, and second derivative is has a minima at x equal to 0. So, as I said before, please try the problem yourself first before you continue the video. So that you will see that how much you have understood. This is more or less a direct question from the lecture's video actually. So the solution. So we know that for such a sandwich geometry, the solution is given by Cb is equal to Mb by 2 root pi dBt exponential minus x square by 4 dBt. And now, so this is how the geometry looks like. So question is about the profiles. So if you see that the Cb has a profile like this, this is the concentration, the maximum is at x equal to 0. So the first option, that it is a symmetric about x equal to 0, is correct, because both the materials on the side are same, and the length and the dimensions are same, hence the profile is also same. Second option was that whether the dou Cb by dou x, the first derivative, is symmetric about x equal to 0, or the third option was whether it is anti-symmetric about x equal to 0. So as you can clearly see here that the quadrant to the sign of the dou Cb by dou x changes from this quadrant to the quadrant here. So here it is positive, whereas here it is negative. So therefore this is not a symmetric about x equal to 0, but it is rather anti-symmetric. So whatever is the amplitude here, it is the amplitude here also, but in the opposite sign. So therefore the correct thing is that it is anti-symmetric about x equal to 0. Then about the second derivative, if you plot, you can very clearly see that there is a minima at x equal to 0. So the correct options for these questions are A, C and D. As I have already told that in assignments or in your exams, you can expect multiple choice questions where more than one correct answers are there, and you need to mark all the correct answers in order to secure marks. Moving to the second question. So refer to the given profiles which are developed during a carburization process as a function of annealing times T1, T2 and T3, and if x1, x2, x3 are the corresponding penetration depth, select the correct statements. So one statement is about the time. So you can see this is the profile. So here if you see that we know that higher is the penetration depth, more is the time required, or other way, if you anneal for a more time, you will achieve a higher penetration depth. So therefore from here we can see that the depth in the case of T1 is less, it increases to T2 and then further to T3. So therefore the correct relation in this case is T1 is less than T2 is less than T3. The equation that governs this profile is C of x comma t minus C naught by Cs minus C naught is equal to 1 minus error function x by 2 root dBt. And if everything else is same, then we know that x1 square by t1 is equal to x2 square by t2 is equal to x3 square by t3. And therefore, you see that the option C is also correct. So, basically here the correct options are B and C. Now, the question number 3 is something that is an application of what we have learned in the class. Sketch the concentration profile for the case of decarburization and write the corresponding solution. So, we talked about carburization, where a surface concentration of carbon is maintained by maintaining a flow of gas, but sometimes you also need to get rid of carbon at the surface. So, that is process is known as decarburization. And decarburization, so how would we write the solution and how do we sketch the profile? Actually, writing the solution is fairly simple if you know already the solution for the carburization. So, in the carburization, we wrote C of x comma t minus C naught by Cs minus C naught is equal to 1 minus error function x by 2 root dt. Now, in decarburization, typically you want that at the surface your carbon concentration is 0. So, if Cs is 0, just simply put Cs equal to 0 in this equation and you will get C of x comma t is equal to C naught error function of x by 2 root dt. So, this is the solution. And how would the profile look like is something like this. At Cs, at the surface, Cs is equal to 0 and then it increases as you reach the bulk where it is C naught. So, this is how the decarburization profile would look like. Now, here this is a question where it is again based on a thin film diffusion problem. So, the question reads like this: a small quantity of gold was deposited on the end of a cylinder of a metal M. After holding for 48 hours at a high enough temperature, the specimen was sectioned and the concentration of each slice was as mentioned in the table below. Use this data to determine D. Now, here there are a couple of ways to solve the problem. I will tell you one and I will request you to find out the other way of solving this problem and maybe post it on the forum or share with us once you find out. So, what is given is that distance from the end of a bar of is here in microns and the concentration is given here. So, basically it's a thin film condition with only one direction where the diffusion is happening. So, the solution can be written as Cb of x comma t is equal to mb by root pi dbt exponential minus x square by 4 dbt. And if you take log both the sides and you have log of Cb is equal to log of C naught minus x square by 4 dbt. Therefore, if I plot log Cb versus x square, the slope of this will give me minus 1 by 4 dbt, or in other words dB will be equal to minus 1 by 4 into slope into t. I know the t, how do I find the slope?
So, now the question is that how do we find the slope of this? So, there are more than one ways of finding the slope. One way that I have done here is basically to take this data and plot it in a software. For example, in Origin or in Excel. I have done it in Excel here. So, you have the concentration here and you have the x here. And we see that the log Cb is equal to log C naught minus x square by 4 dBt. So, what I have to do is I have to plot log Cb versus x square. So, when I do that, I get a profile like this, I get a figure like this, where these are the points here and this is the fitted line. So, you can see that this is the slope which is a negative value which is expected, which is also indicated here. And once you have got the slope here, we can then use it to calculate. For example, here the slope is minus 9 into 10 to the power 8 per meter square. And we are given the time of annealing equal to 48 hours. So, therefore, the diffusion coefficient, if we now put in this formula, we get the value of 1.61 into 10 power minus 15 meter square per second.
Now, moving ahead for the question number 5, what you see is that an FCC iron carbon alloy initially containing 0.1 weight percent carbon is carburized at an elevated temperature and in an atmosphere wherein the surface carbon concentration is maintained at 1.1 weight percent. If after 48 hours the concentration of carbon is 0.3 at a position 3.5 mm below the surface, determine the temperature at which the treatment was carried out. So, for carbon diffusion in FCC iron, D0 is given as this, Q is given as this, and error function of Z you can assume to be equal to Z. This assumption is reasonably okay for solving problems without referring to the table as such. So, we know that for the carburization problem, the solution is given by C of x comma t minus C naught divided by Cs minus C naught is equal to 1 minus error function x by 2 root dt, and the C naught is equal to 0.1 weight percent, Cs is 1.1 weight percent. It is the surface carbon concentration is maintained at 1.1, so that Cs is 1.1 weight percent, and C of x comma t, that means it's the composition of the interest. This is the here mentioned, and x equal to 3.5 mm, convert it into meters, time is equal to 48 hours. So, if you put everything here, what you get is, and assuming that error function of Z is almost equal to Z, what you get is x by 2 root dBT is equal to 0.8. And if you put all the values in the correct units, remember it is very important to put the quantities in the correct units when you are solving these problems, otherwise you may end up in getting unrealistic values. So, if you solve this, you will get dB is equal to 2.75 into 10 power minus 11 meter square per second. Now, this directly, so far we have not come to this equation, but just let me tell you that diffusion coefficient does depend on temperature, and it follows an exponential function, which is dB is equal to dB naught exponential minus Q by RT. Because remember, in our question that is stated is determine the temperature at which the treatment was carried out. And what we are given is D naught, which is known as pre-exponential factor, and Q, which is the activation energy. So, this is how the relation goes. dB is equal to dB naught exponential minus Q by RT, and now we are given we are given dB naught. We just found out what is dB, and this is the value of Q in kilojoules. We need to convert into joules. So, multiply by 1000. And this R is the universal gas constant, which is 8.314 joule per mole Kelvin. So, if you put all the given values here, you get temperature approximately 1305 Kelvin. Question number 6 is also based on the carburization. So, here what you are basically given is already the temperature is mentioned. The carbon concentration, uniform carbon concentration is 0.25, which is equal to C naught, and the concentration of carbon at the surface is maintained at 1.2, so that is Cs. And how long it will take to achieve a carbon content of 0.8 at a position 0.5, so mm. So, this C of x comma t is given as 0.8 and x is given as 0.5 mm. And this is the value of D given here, 1.6 into 10 power minus 11 meter square per second. So, if you put this here, and again for the sake of easy calculations, I have told you that assume that error function of Z is Z. So, what you get is x by 2 root dt is equal to 0.42, and if you solve for t, you will get 3.8 hours. Okay. Even if let us say you leave the options in seconds, it is okay, but it is generally good to write it in hours. Now, the 7th question, it looks like a carburization question, but actually if you will see, it is not a carburization question. So the question is, a plate of iron is exposed to a carburizing atmosphere on one side and a decarburizing atmosphere on the other side at 700 degree centigrade. If a condition of steady state is achieved, calculate the diffusion flux of carbon through the plate if the concentrations of carbon at positions of 5 and 10 mm beneath the carburizing surface are 1.2 and 0.8 kilojoule kg per meter cube, and assume a diffusion coefficient of 3 into 10 power minus 11 meter square per second. So if you sketch this problem, it is like this. So your plate of iron, on one side you have a carburizing atmosphere, that means you have a higher concentration here, and you have a decarburizing atmosphere, you have a very low concentration here. And given that the steady state is achieved, that means this gradient is not changing. You have also achieved a steady state, means this carburizing and decarburizing atmosphere are maintained in such a way that the concentration gradients are not changing. That is what you remember, that we see that dou C by dou T is equal to 0. So that means now what is given is, at a position of 5 mm below the surface, you have a concentration 1.2, let me just call it as Ca, and another at 10 millimeter depth you have 0.8, let me call it Cb. So now, because it is a steady state, in order to calculate the flux, I can directly use the Fick's first law, because dou C by dou T is 0. I can directly use Fick's first law and write J is equal to minus D times dou C by dou X. So D is given 3 into 10 power minus 11, and dou C by dou X is nothing but Ca minus Cb by Xa minus Xb. Now here J is equal to, you just put the values. So what you end up is 2.4 into 10 power minus 9 kg per meter square second. So I hope it is clear. How do you apply the Fick's first law here? Now another problem, I think perhaps the last of this tutorial. So suppose that a diffusion couple is formed by welding together of two alloys of elements A and B, having the compositions 40% of element A to the right of the weld and 50% of element A to the left of the weld. Many of these problems, they are long to read, but actually if you draw, you can draw very nicely, and then it is much easier to solve. So let this couple be heated quickly to some temperature T and held at 40 hours. And after cooling to room temperature, chemical analysis shows that at a distance of 20 into 10 power minus 3 meters to the right of the weld, the composition is 42.5% A. Now find the diffusivity, and then with the assumption of a constant diffusivity and the same diffusion temperature, compute the time required to obtain the same composition at twice the distance from the weld surface. Again, assume error function of Z is Z. So this is how the problem looks like. See, here you have two alloys of elements A and B having compositions 40% to the right. So I have written it as Ca minus, because this side is slightly leaner in A, and here I have written as Ca plus, it is equal to 0.5, which is slightly enriched in A. Not enriched, compared to the right side it is more, because Ca equal to 0.5 means B is also 0.5. So when this couple is heated at a certain temperature for 40 hours, what will happen is that A will start diffusing from this side to this side, from left to right, because of the concentration difference. And the situation which is given after 40 hours is here. Basically, at a distance of 20 into 10 power minus 3, you have the chemical analysis shows that the composition is 42.5% A. I have written it in fraction as 0.425. So now what we need to do is we need to find the diffusivity. So we have seen that for the expression we have derived when the diffusing element was initially present only on one side. That means the case that we saw, in which one side it was a alloy of, let's say, A and B, on another side it is pure A. Okay, so it was one side a pure element, another side an alloy. So that time the solution that we have written is C of x comma t is equal to C naught by 2 1 minus error function of x by 2 root dt. Now the only change that has happened is that both the sides now there are alloys. Okay, so in that case the solution is modified like this. So C of x is equal to Ca plus Ca minus by 2 minus Ca plus minus Ca minus by 2 error function x by 2 root dt. You can check here that if Ca minus is 0, it will basically you will come to the same solution. So or Ca plus, in this case, if it is 0 on one side, if you have 0, then it will come to the same solution. So here now if I put the value of 0.5 here and 0.4 here, and then Cbx is 0.425, then you put these values here, assume that error function of z is almost equal to z, so you get x by 2 root dt as it is. So you get x by 2 root dt is equal to 0.5, and when you solve this by putting the various values which are given, you will see that d is 2.7 into 10 power minus 9 meters square per second. Remember to put t in correct units, it is 40 hours, so you have to convert it into seconds. So this is how the solution can be arrived at here, and so we have seen already some examples. Please practice further and do the assignments, and if you have any further doubts, please feel free to put it in the forum. So with that, we'll end this tutorial lecture. Oh, sorry, I think I forgot. There is a small part here to be done, that if everything else is same, then given that x2 is equal to twice x1, that means how much time you need to double achieve the same concentration at double the penetration depth. So we need to see that x1 square by t1 is equal to 4x1 square by 4x2 square by t2, and t2 is equal to 4 times of t1. So t2 is equal to 160 hours. So with that, thank you everyone. Then we'll see in the next video.